Hi friends, this is a PH 5502 Unit 4 lecture on electrical property, lecture number 8. Well, the electrical property for especially the metallic material, so we are not touching the other crystalline structures. As we are aware, fundamentally there is a three types of bonds are there. So covalent crystals could be there, ionic crystals could be there, and the metallic crystals too could be there. So among this all the varieties, presently we are just discussing rather the metallic property, metallic crystals only we are discussing. So as I highlighted over here, the electrical current density in the steady state is proportional to the electric field strength, that is nothing but the Ohm's law. It is also find especially in the metallic crystal that a pure specimen, then the electrical conductivity, that is on an average referred as a sigma, and the thermal conductivity varies with the temperature. Either you highlight the resistivity or you highlight the conductivity. Okay. So, this author has highlighted the conductivity. So, conductivity is proportional to 10 to the power minus 1. So, it is in short, conductivity is inversely proportional to the temperature, and here the temperature, that means as the temperature is rise up, the conductivity should go down, or the resistivity should rise up, but that is only true for the temperature which is higher than the Debye temperature. Theta d is I think in SYBSC we had come across with the two kind of the models. One is the Einstein model and second is the Debye model, and Debye model is considered to be the better model, better fitment of with the theoretical aspects and so on. So anyway, so that is in short, it's a higher temperature range. For a low temperature range, that means when you are approaching to the 0, the behaviors are quite weird and different than what you have seen in your normal temperature range and so on, even at a low temperature. But when you are going very much below low temperature, so I should say it's a T very much lesser than the Debye temperature, that means your temperature is quite low, maybe in 0 to 10 Kelvin. So your behavior will be not following the inverse law function, but it is something else, and that is 10 to it is observed empirically that it is the 10 to the power minus 5 behavior, whereas sigma t is belongs to 10 to the power minus a. The noticeable information is over here. The electrical conductivity varies with the 10 to the power minus 5 time, whereas the thermal conductivity varies with the variation of just power 10 to the power minus 2. So, over here the sigma t, that is the thermal conductivity, is almost remain constant for a higher range of a temperature, and when you go with the very below low temperature, it is just varied by 10 to the power minus. So, the variation in the thermal conductivity is less, variation in the electrical conductivity is drastic, right, and thus that is how you can say that in the normal or moderated range of thermal conductivity and electrical conductivity, they are quite behave identical, but at a low temperature they are not behaving similar trend, or they are not behaving identically. Okay. This sigma 10 to the power minus 5, that relation, or sigma raised to 10 to the power plus 5 is known as the Bloch-Grunewsen law. So, that is for just information. The ratio of electrical conductivity to the thermal conductivity. So, sorry, the thermal conductivity to the electrical conductivity. So, sigma t upon T, that is known as a Weidmann-Franz law, and over there a very nice interesting inputs comes out, we will see later on. Okay, so that is just input. So what we have observed over here, in case of a metallic crystal, the resistivity having a two segment. One is independent of a temperature, another is dependent on the temperature. Sigma is a rho is a considered to be the resistivity inverse of sigma, and the very first step, that is a rho 0, which is referred as a residual resistivity, and it is independent of temperature. So it is written it is a constant and it is increases with the only impurity. So by chance, let us we think about the alloy and so on. So when you are going to add some impurity in your metal, then the rho has to change. Secondly, suppose your crystal having a certain foreign material and foreign body and so on, so that is also considered to be impurity, but in nutshell that is a constant part which is independent of a temperature, whereas the rho p stand for phonon, it may be written somewhere, and that is depend on the temperature. Okay, and this is rho of rho 0 plus rho p suffix t. So p is basically known as a phonon. Phonon is basically arises because of your host ion or the atomic oscillations, and that is this law is referred as a Matheson's rule, Matheson's apostrophe S, Matheson's rules. Looking to this particular relations, if I will draw a curve rho versus t, rho on y axis and t is on x axis, then if it is a pure one, then it has to pass through the origin. But suppose you have an impure something, so the residual, that is the first step of your equation, Matheson rules, that will be shifted a little bit. That means this part is referred as a residual. So I should write a rho 0 over here. Are you getting me? This is rho 0 increases by adding a more impurity. तो इसमें impurity थी, मैंने थोड़ी और impurity add की. Let us say I am making alloy. So residual resistivity, that is rho 0, will increases. Okay, and what are rho into 10 to the power minus 7 ohm meter, that is on I am taking x axis, and on y axis I am taking a concentration of the impurity. So अगर मैं impurity add करते ही जा रहा हूँ तो residual resistivity बढ़ती जा रही है. So the behavior of iron is more stiffer compared to the nickel, and silver is so lenient. So this also suggests that the response of addition of an impurity into the metallic crystals, they behave independently from one metallic crystal to the another metallic crystal. So there is nothing like a standard relation between the addition of a impurity to the response of the resistivity with respect to the temperature, because here you can say that in case of a Ag the slope is little bit less, the nickel is better slope, in iron it is a stiffer. So addition of an impurity of let us say 0.005% in case of Ag, the very less improvement on rho, but in case of over here nickel is very highly and this is very high. So something like that one can understand it. Okay, in continuation of this, there is basically two types of lattice imperfection, and which can contribute the electrical resistivity. So the Matheson's rules, what we are saying, that the first part is a rho 0. So rho 0 is the independent of temperature, but then it is written rho p, and p, that is basically a rho is arises because of the phonon vibrations, or you can say the lattice part. So what are the contributing of the second factor of Matheson's rules? So that we want to just make a discussion over here. So two main types of the lattice imperfection which can contribute to the electrical resistivity. Number one, the thermal vibration of a lattice. That means the lattice, that means the point where you are having the host ion of a metal crystal or the atomic oscillations, which will prevent the atoms from ever all being on their correct site at the same time. So, because of that thermal vibrations, there is a continuous atomic vibrations are there. And second point, they are underlining the presence of impurity atoms, and the other point, defect, that will upset the lattice periodicity. So, this is also try to be understood, that suppose an impure material is added into a crystal, or by default it is impurity is there, then the size of your atomic size of your impurity is differ, and therefore your lattice pattern become weird. It won't be like a very standard periodicity will be there. One atom is little bit larger. So, from that particular point your periodicity is slightly deviated, and because of this deviation as well as the thermal vibration of this one. So, the increment of Matheson's rule point number 2, that is rho p. So, the lattice vibrations or the temperature dependent component of a resistivity is depend on a two part. One is a thermal vibration and second one is the impurity atoms, which creates the defect, a permanent defect in your lattice pattern and periodicity, and that is how the lattice vibrations will affect, and therefore the resistivity. Let us try to make a equation for this. If m is a mass of an atom and f of x I consider as a I'm sorry, not f of x, fx is considered to be the restoring force, then this relations will give me the equation for the atomic harmonic oscillators. Divide the equation by m, then I can having a accelerations, and this is the f by m, x is equal to 0 in the steady state relation. So, that I can correlate with the omega, and this second factor will give me the about the amplitude vibrations, and ultimately I am able to develop the 1/2 kx square. So, that relation will give me the relation for the potential energy, and potential energy will be able to deduce with the help of this relations. Anyway, so the further I am not going to be detailed on the mathematical, it is for the mathematical development. And finally, x square is equal to h square t upon m mass. This is Boltzmann constant, Planck constant, this all are the constant parameter. Well, d by temperature for a certain set of metallic crystal, that is also remain constant. So, only the variable parameter, that is only t. So, the next final equation I am able to produce, that is a scattering cross sections, and that would be qf, that is a certain constant, or actually ideally one should think about the scattering cross section is proportional to the square of amplitudes, and yeah, it is written here, see, proportional to the square of the amplitude, and therefore it is a x square. So, scattering cross sectional is multiplied with the certain constants, and finally we are able to get the mean free path, and once you have a mean free path, you may having the relaxation time in terms of the amplitude. So, it is a 1 over n nu x square. Okay. So, from that particular tau, I can having the calculation of tau f, that is a Fermi relaxation time, and from once you having the Fermi relaxation time, Fermi velocity and Fermi mean free path. So, ultimately lambda is inversely proportional to with the temperature, that I also highlighted over here, and therefore, ultimately sigma is inversely proportional to the temperature. That is what in the beginning we had calculated, but this is only true for the range, for the higher range of a d by temperature. In short, we are not touching to the lower range of a temperature, because as we had said that the electrical conductivity and their behavior are little bit different at a lower temperature zone. Okay. So, if sigma is inversely proportional to the temperature, so I can say that, you can look at here again, let me take you back there. then sigma is inversely proportional to the T, then naturally I can say that the conductivity resistivity is proportional to the temperature, and therefore, the total resistivity again Matheson's rules are come to the picture. So, it is in a two part rho 0 plus rho p as a function of a T. So, if I will draw a figure, this is almost similar figure what we have seen earlier, that was with the conductivity, now we are drawing with the resistivity. So, resistivity, no, I think that also with the resistivity only, right. Let me check the previous graph. So, you may having a more feel that what we have seen the graph is similar to the same one. So, this is the rho versus T only, correct, rho versus temperature. So, we are talking about the same one, okay. And okay, the next one is rho versus temperature. So, this is the same curve, okay, and this is having a two part rho 0 plus. So, rho 0 is where from where you are begin, and if it is the lower curve is coming through the origin. So, origin, that means rho 0 become 0, that means this is a very pure material, okay, and once you add certain impurity into that, your residual resistivity will increases, or your first step of your Matheson's rule will increases, which is less depend on the temperature. Whereas, the second part of your equation, that is rho p, that is basically scattering phenomenon of the phonon, and that one is showing here as a scattering by phonon. The first horizontal line is showing, and that is basically scattering of impurity. So, here the addition of impurity that remain constant in a given crystalline material, and therefore, that particular scattering phenomenon will remain independent of temperature. So, it shows the horizontal line over here. Anyway, so your inversely proportional to the relaxation time, or your relaxation time is basically, or 1 over tau is basically the summation of two component. One is 1 over tau 0, that is because of an impurity, whatever the variations comes into the relaxation time, and second part is the relaxation time because of the phonon. So, this two component I am adding to the resistivity part. Then resistivity equations, we are knowing that m star upon n square tau 0 for the residual one, and m star upon n square tau p. So, just I am writing out a generality into two components. So, I am writing this, if m star upon n square is a common, 1 upon 1 tau 0 plus 1 upon tau p. So, simplest addition of the rho t and rho p of the t as a function, and that is nothing but the Matheson's rule in terms of the relaxation time. Okay. So, with this we can having one more clarity about it, and let us say here I am adding the impurity. So, this is a purest copper material, but you can see that it is still not passing through the this one. Here it does not mean that we have not add any particular single impurity, because there is some dislocation of atoms are also possible, or maybe during the formation of a crystalline certain defect in a crystalline material, which is always considered to be the independent of a temperature. So, residual resistivity could be strongly caused for the impurity, but it could be also caused because of some permanent impurity or permanent dislocations, and that is why pure Cu also having a certain resistivity. And here I am adding the impurity of a nickel step by step. So, as you have seen in the very first step, first graph, that resistivity versus temperature, resistivity versus percentage of impurity, and you have seen that the graph it becomes steeper or linearly increases. So, as the percentage of addition of this increases, the nickel graph or copper nickel graph is shifted up, that means residual resistivity increases by step of identical jump, and this is a proof that your first step of your Matheson's rules is giving the independent segment of a temperature. So this portion you can see, look at the temperature region is constant, and that is what we are highlighting over here. Okay. So in the next part we are highlighting the few important aspects, that the resistivity of a metal arises due to the scattering of a conduction electron by the lattice vibration, that is because of the phonon scattering, and by the impurity. And as I said, there is some possibility of structural imperfections is possible. So structural imperfection, that means what? Let us say your crystals is hammered by or it may be throbbed by any particular impact, or maybe your crystal is getting a pressure, or maybe your crystal is getting a temperature transition, and certain physical aspects is able to create a structural imperfections. So anyway, so at a low temperature the impurity scattering is dominating compared to the higher temperature. So the resistivity is put it into the three segment. So earlier we have seen that the resistivity is made up of a two part, the independent of a temperature and the dependent of a temperature. Now the further detail of the resistivity tell us that the resistivity could be basically categorized into the three part. One is a rho L, that is called the lattice scattering. Now we are just highlighting the scattering theory. So everything is because of the conduction electron is reaching from a point A to point B, or the consecutive collision between the conduction electrons, and that path is said to be a mean free path, and that particular time phase is referred as a relaxation time. So during this phase, what are the possibilities to scatter the mean free path or the mean free time, or disturbing that, and that is what the impulse to the resistivity. So the very first point is that resistivity could be because of the lattice scattering, माने आपके lattice ये point माने आपका atomic position या host ion की वजह से scattering हो रहा है, the scattering because of your host ion, and which is strongly temperature dependent. Whereas the I, rho I and rho D are not the temperature dependent. So that is rho I, that is the resistivity due to the scattering. We have just seen in the previous graph that impurity is increases, then that region was remain almost independent of a temperature, and it was not affecting to the temperature. So the impurity contribution is just shifting on your y axis. Okay. So I'm sorry, yeah, so that is there, the I is contributing the impurity contribution, which is again independent of a temperature, and D is a permanent deformation in a crystal. So basically it is a part of a impurity, but it's a subcategory of a impurity. That, as I said, that impurity, that means in general we have understand that a foreign atom is within your material. So a non-identical periodicity will arise this because of that. Ab और एक deformation, impurity is kind of also of a deformation in a periodicity. The rho D, that is a permanent defect. Okay, and maybe a physical impact, maybe a reorientation of a atomic situation, or maybe a temperature gradient is delocate the host ion and so on. So certain stresses, maybe a temperature stress, maybe the physical stress, will be a cause of the defect, and that is called a permanent defect, which is still again independent of a temperature. So looking to the rho, which is subcategorized into the three part, initially Matheson's rule says that it's a two part. One is a independent of temperature, that is rho 0, and then it's a rho p. Now this we are talking about the rho is not even a two part, but it is categorized in a three part. the independent of a temperature, that is of carries two component, and temperature dependent carries a one component, that is still a lattice vibrations or a lattice scattering. सो दिस इज़ एक्चुअली मैथेसिन्स रूल्स की अगर बात करें तो ये मेरा पार्ट 2 हुआ, और ये पार्ट 1 माने रो ज़ीरो इज़ कंट्रीब्यूटिंग टू कंपोनेंट रो आई एंड रो डी. डी इज़ अ डी लोकेशन, आई इज़ अ impurity. Okay, so further understanding of the scattering theory of or the conduction electron scattering theory to understand the electrical conductivity, we says that the probability, we are introducing a new concept. Unfortunately, the author has taken the rho s again. This rho s doesn't have any correlation with the resistivity. Please remember, so I am highlighting over here, rho s is the probability scattering. It's a probability of a scattering. Okay, so please take a note of it. And this probability of a scattering is inversely proportional to your relaxation time. Okay, so as the relaxation time is higher, that means your probability scattering is less. Okay, it's a pure statistical conceptual idea, it is just put forward over here. Okay, now we know the conductivity. Conduct is to be honest, this m could be ideally m star, and as I told you in the last lectures, that m star is basically arises with the concept that when your conducting electron is passing near to the vicinity of a host ion, their velocity will changes, and the change of this velocity is indicate to mimic that there is a variation in the mass. So ultimately, from the empirical survey, this theoretical model has made one corrections, because out of this all the four parameters, n is fixed, e is fixed, tau is for the situation is fixed, then why the conductivity is changing? So only the one correcting factors which is going to be corrected, and that is a mass of electron. So अगर इलेक्ट्रॉन होस्ट आयन की विसिनिटी में से पास हो रहा है तो वहाँ न्यूक्लियर अट्रैक्शन की वजह से थोड़ी उसकी स्पीड कम हो जाएगी. तो स्पीड कम होना माने उस सिचुएशन में देयर इज़ ओनली वन कंडीशन इज़ अंडरस्टैंडेबल, दैट उस अगर ऐसा सोच लो कि वो पार्टिकल थोड़ा हेवियर हो तो वहाँ पे उसकी वेलोसिटी कम हो सकती है, एंड वे दैट्स वाई द न्यू कंसेप्ट हैज़ इंट्रोड्यूस, दैट इज़ अ एम स्टार. So ideally it should be m star. I think the resistivity में आपने देखा, it would be m star upon n square tau. Okay, so that is there. So rho s is the probability of a scattering. So probability of a scattering is basically depend on its velocity. सो इसमें और एक इंट्रोड्यूस किया प्रोबेबिलिटी पर यूनिट लेंथ. सो मैंने एक यूनिट फैक्टर डाला है कि पर यूनिट लेंथ ऑफ माय मीन फ्री पाथ देयर इज़ अ पॉसिबिलिटी ऑफ अ स्कैटरिंग, राइट. सो what is basically a mean free path? The distance traveled by a conducting electron between the two consecutive collisions. Within these two consecutive collisions, when electrons is freely moving from point A to point B, whether it is get scattered or not. Now during this motion of a two consecutive collision, it's having a velocity, it having a certain velocity. This velocity will be very high, maybe a maximum equivalent to the Fermi velocity, or over here if they have taken the velocity or their average velocity for all conducting electrons, so I am writing V0, and as it is written, it is corresponding to the Fermi energy. And so sometime you can refer as a Fermi velocity as well, no problem. Anyway, so that velocity should multiply by with the scattering probability per unit length. Okay, that is sigma suffix s. Scattering probability per unit length. Scattering probability per unit length. Okay, and that is what over here. Okay, so Now as you are aware that relaxation time is inversely proportional with the probability of the rho s, that what we have seen in the previous relation. Let me take you there. Tau is 1 over rho s. Rho s is the probability scattering, and probability scattering we have seen that it is sigma s upon sigma s into Fermi velocity or the mean velocity. So it's a 1 over sigma s v0. Remind you again, sigma s is nothing but the scattering probability per unit length. एक यूनिट लेंथ डिस्टेंस ट्रैवल कर रहा है तो उसमें उसको स्कैटरिंग होने की प्रोबेबिलिटी कितनी है, मल्टीप्लाई बाय इट्स मीन वेलोसिटी, एंड दैट इज़ व्हाट द मीन ऑफ सिग्मा एस, एंड सिग्मा एस इंटू वी ज़ीरो करो तो आपको रो एस मिलेगा, एंड रो एस हैविंग अ रिलेशन विद द इनवर्स प्रोपोर्शन विद द टाउ. So anyway, so ultimately I get the scattering probability per unit length is given by proportional to ns. What is ns? It is a scattering constant centers per unit volume. So as I highlighted here, the calculation of a sigma s, that is a scattering probability per unit length, is very difficult to figure out, and therefore it's need to be approximated. So scattering कहाँ पे highest होगा, जहाँ पे उसका volume highest होगा, है ना. So they said that the sigma s is proportional to the number of scattering centers per unit volume. So how many scattering centers per unit volume you have, and according to that you will having a strong probability of a sigma s. Are you getting me? So if ns is high, then naturally sigma s will be high. So in nutshell, sigma s is directly proportional to the center per unit volumes, or the scattering centers per unit volumes. What is scattering centers? Nothing but the host ions. Okay. And when you remove the proportionality constant, you having a scattering cross section. So if you take a tangential cross sectional area or per unit cross sectional area, how many number of the centers or the scattering centers you are coming, and that is will give you the proportionality constant. So scattering cross section per centers. So per cross section how many centers you are aware, and that will be multiplied by the number of volumes, and that will give you the probability of scattering cross section per unit length. Okay, so ultimately tau is restructured in an equation of 1 over v0 sigma s ns. v0 is a mean velocity, sigma s is a scattering cross section per unit center, and ns is the scattering centers per unit volume. So ultimately we said that tau is inversely proportional to this. Any variations in a value of a tau is only due to the scattering cross section per centers, since v0 and ns is almost constant for a given metal. As I said that ns is a number of the scattering centers per unit वॉल्यूम, माने एक वॉल्यूम में कितने नंबर ऑफ होस्ट आयन है वो तो फिक्स ही हुआ. सो नंबर ऑफ अवेलेबल ऑफ एन एस इज प्री डिफाइंड व्हेन यू विल चूज द मेटल. सो अल्टीमेटली एन एस इज अ कांस्टेंट फॉर अ गिवन मेटल. दूसरा आ रहा है V0. सो V0 इज ऑल्सो कांस्टेंट because for any structure material number of available of electrons near the Fermi energy is also fixed, and number of our Fermi energy is fixed. That means the given thrust to the conducting electron, that is also fixed. So your aapki mean velocity is also constant. So only the sensitive parameters, that is a sigma s, and sigma s is again in a way it's a constant or proportional constant, and that is a scattering cross section per centers. So basically the scattering cross section of a center, that means you can say that it's a exposure area. So, when an electron will pass, what is the exposure area it is getting when it is passing through a host ion or a scatter, let me use the technical word as the author has used, then it's a scattering cross centers. So, when it will passing through the scattering cross centers, what is the cross sections per centers it is available, that is also. So, ultimately sigma s is directly proportional to the square of the amplitude. So, sigma s is directly proportional to the square of amplitude of a lattice vibrations, because as the lattice will vibrating a lot, your cross sectional area और स्कैटरिंग क्रॉस सेक्शनल एरिया विल बी लार्जर. आप सोच लो कि एक एटम अपनी होस्ट पोजीशन पे वाइब्रेट हो रहा है. सो एटम इज कवरिंग अ सर्टन रीजन. सो नेचुरली व्हेन इलेक्ट्रॉन विल पास थ्रू द विसिनिटी ऑफ दैट, it come across with the larger cross sectional area, and larger cross sectional area, that's why I can say that sigma s is proportional to the square of amplitude. Okay, and therefore sigma s is proportional to temperature, and so far tau is inversely proportional to the temperature. Okay, with this finally I can say that the sigma s, that is a scattering cross section, or rather a probability, sigma s is a probability, scattering probability per unit length, that is a sigma s, which is we had said it's a difficult to measure it, and this all the following steps we have done for the measuring the scattering probability of a scattering per unit length. Probability of a scattering per unit length is summarized into the three part: scattering because of a lattice, scattering probability because of imperfection and impurity, and scattering probability because of a delocalized periodicity or permanently defect in the crystal. And since sigma s is directly proportional to the t, or the tau is inversely proportional to the tau, I can say 1 over tau is equal to, or if you do remember, we had mentioned that the tau is directly proportional to the sigma s, and therefore sigma s we can directly write like this. So, sigma s when you correlate with the tau, it ultimately V0 into the probability of a cross sectional, probability of a per unit length, and therefore rho is again become the m upon n square tau, and therefore this 1 over tau is replaced from the above relation. So, this equation will arise, and ultimately we can able to achieve the same relation, that is a rho by L, rho by impurity, and rho by D, that is a cross scattering probability by lattice, scattering probability by impurity, scattering probability by permanent defect. So, with this we end up the scattering theory of the conducting electron. The next topic is thermal conductivity. Thermal conductivity we are knowing from very fundamental level, from the 11th and 12th grade understanding, that basically it's a conduction of a heat, or conduction of a transfers of a thermal energy from a point A to point B. So, in general it is observed that it is a hot body to a cold body, the energy will be transfers. So, let us say the amount of a thermal energy Q which crosses a unit area of a bar per unit time, that is given by the heat flux. So, J of Q is directly proportional to the rate of change of temperature, and x is your length of your sample, and dt is your change of your temperature or temperature gradient. And when you remove this proportionality sign, that would be sigma t. So, sigma t is referred as a thermal conductivity. Okay. So, this thermal conductivity having a negative sign because the heat is flowing from the hotter portion to the cold portion. Okay. So, the unit of conductivity, heat conductivity is also given by watt per meter Kelvin. So, this is from this also you can transfers of a heat per unit length per unit temperature. So, transfers of a heat per unit so if you say J by Q, whose JQ or the thermal conduction heat conduction is having a unit watt, and watt divided by dt by dx, so the unit become watt per meter per Kelvin. Okay. It is also observed that the thermal conductivity decreases with the increasing of temperature. It is very obvious that when you having a temperature gradient is lesser, so naturally JQ is directly proportional to the temperature gradient of your given sample. So, if your size of your sample is lesser temperature gradient, so naturally it should be lesser. One more important points I highlighted over here in the yellow, that in case of an insulating material, the heat is carried by almost the vibrations of a lattice or the phonon. But in case of a conducting metal, especially in the metallic crystals, the scenario is little bit different. The transportation is taken place by a two entity, one is a phonon and second one is a electron. Now, if we look at to the magnitude of the contribution of a electron conduction and contribution of a phonon conduction, then we have observed that the contribution of the phonon is very less in case of a thermal conductivity as well as in case of a electrical conductivity, especially in the metallic crystal. So, in general, sigma T, that is a thermal conductivity having a two part, one is a thermal conductivity carries by electron and thermal conductivity carries by conduction taken place by the phonon. And if you look at to the magnitude of it, then look at here, sigma P is 10 to the power minus 2 of 2 times of the sigma electron. That means compared to the electron contribution, the sigma P is very small, and therefore sometime for a better understanding it is neglected as well. अब यहाँ पे क्यों हो रहा है? Why the temperature gradient, let us say T2 and T1, T2 is greater than T1, so ये आपका hot end हुआ बार का और ये आपका हुआ cool end. So, why there is a heat is flowing from higher hotter to cooler. So, the available number of electrons are on the cooler temperature and the available number of electrons on the hotter are little bit different, right, because we had already seen a variation of transition of a electron from a conduction valence band to the conduction band with respect to the temperature, because they are follows the Fermion's law, and that is a Fermi-Dirac distribution. So, as there will be a higher temperature, naturally there is a more amount of electrons are taking participation. So, first of all I should say that here there is a possibility of a little bit more concentrated electrons are here compared to this. So, in this Fermi energy level at a higher temperature range, there is a little bit more concentration of electron compared to this. Okay. Now, they are doing a random motion on near to the Fermi surface, and here also they are doing in a random motion, but there is a little bit net flow in a direction of towards the cool direction. Similarly, here also you can say that there is some certain net flow in the direction of a hotter one, but the amount of heat from hotter to cooler is little bit higher compared to the cooler to hotter, and therefore a net flow is taken place because of from a T2 to T1 or a hotter end to the cooler end. The electron at a hot end travels in the old direction, but at a certain fraction travel to a right and carries energy to the cold end. Similarly, there is a certain fraction of an electron at a cold end travel towards the left and carries the energy to the hot end. This oppositely traveling electron current are equal, but because of those at the hot end are little bit more energized on the average than those on the right hand side, a net energy is transported towards the right. Okay. So, available number of electrons could be similar, number of dots over here and number of dots are here are equal, but still there is a, this is more hot, so they are having a more energy. As I said that the electron, the Fermi energy near to the Fermi energy electrons are getting a little bit more energy and they are driving to the कंडक्शन बेन माने थोड़े इलेक्ट्रॉन उसकी हाई एनर्जी स्टेट में चले जाएंगे. सो अवेलेबल नंबर ऑफ, there is also possible there is little bit more number of electrons are also here, but they travels oppositely. So the amount of a current traveling from T2 to T1 is little bit higher than the amount of a current travel from T1 to T2, and therefore the net flow will be in the one direction, that is hot to cold, and that's why the negative sign. Since they are close to the Fermi energy surface, so it's a 1/2 m Vf square is equal to Ef, and from that relations we can able to calculate the sigma t. Sigma t carries the 1/3 factor is because of the degree of freedom, specific heat because of the electron contribution, this is net velocity of electron multiplied by mean free path. And with this substituting their all the values, we are able to get the sigma t is equal to pi square by 3 n Boltzmann square of the Boltzmann constant, temperature and the relaxation time divided by the mass of electron. Okay. So, it is again mathematical development, nothing to worry at all. But now we are taking the ratio of the thermal conductivity to the electrical conductivity, the sigma t upon sigma. So, ratio of sigma t upon sigma, we are getting a just a few numbers, pi square by 3. So, it is basically constant multiply by square of another constant, Boltzmann constant to the charge of electron into temperature. So, if I say the sigma t upon thermal conductivity upon electrical conductivity is directly proportional to the temperature, and this is an fabulous outcome relation which is referred as the Wiedemann-Franz law. You may have a experiment in MSc or maybe in the TY. I think TY में तो हमारा यहाँ पे नहीं है, but we have introduced the Wiedemann-Franz law in the MSc. Okay, so this particular constant part is replaced by a one number, and that is referred as pi square by 3 k by e all raised to square. This is referred as a Lorentz number, and the beauty part over here is there is nothing like a mass of an electron, there is nothing like a concentration of an electron, everything is cancelled out. That means for each and every metal the Lorentz number is remain almost fixed. Am I right? Because there is nothing like a n, nothing like a mass, now not all depend on the constant. But it is observed that majority of the metals are agree to this, and there is an observation table also I had attached over here as it is given in the book. But the conclusion part is that the electrical and thermal conductivity are closely related because they are basically carried by either a lattice vibration or a conducting electron, especially in the case of metallic crystal. And this is a few example of a few metals, and this is sigma, and this is that is electrical conductivity, thermal conductivity, and ratio of it, and that is you can see it's remain almost constant, right? 2.3, 2.2, 2.3, 2.4, 2.4 and so on. And at a higher temperature, if you look at here, the variations are almost constant, but still if you are notice little bit compared to the higher temperature, when you go to the lower temperature, the Lorentz number is slightly decreases. So as I told in the beginning, it is definitely true that the electrical conductivity of a metallic crystal and thermal conductivity of metallic crystals are depend on the uh, scattering theory, and henceforth it is depend on the uh, lattice scattering by the phonons and the scattering by the electrons. But at the same time, at a low temperature, the change in the scattering cross section area of a phonon and scattering cross section area of the electron are different, and therefore, or you can say that, as I highlighted over here, the relaxation time change in the thermal conductivity and the electrical conductivity are not identical, and ultimately scattering theory is do depend on the relaxation time. अब दोनों के relaxation time temperature zone में अलग अलग आ रहे हैं, and therefore their scattering behavior will be different, and therefore there is a little bit decrement in the case of a Lorentz number. With this, I stop here with the last slide, that ultimately the thermal conductivity will be given as a part of 1 over sigma I versus 1 over sigma L. If you do remember, then the third part was a defect is not prominent over here, because the thermal conductivity is less sensitive to the defect, because the change in the temperature for the larger range of a temperature, the thermal conductivity is remain almost constant. At a lower temperature it is slightly vary, so the defects is not playing a major role. So you having only two dependent component, that is sigma I and sigma L. Remember that this is not at all the this is not at all the conductivity alone, but sigma L representing the contribution arises from the electron lattice scattering, and sigma I is contributing from the electron impurity scattering. With this, I am again changing a last two topic. One is a thermal expansion, and thermal expansions, we are knowing that the thermal expansions of a solid in the most common effect of a heat, and according to this property all solids get increases their size when they are heated up. Okay, and I think the railway track example is a well known, we are learning since from the 11th standard, that रेलवे की दो पटरी के बीच में थोड़ा गैप रखते हैं, बिकॉज ऑफ इन द विंटर इट गेट कॉन्ट्रैक्ट एंड इन summer it get expanded. Anyway, but just for your input, nowadays this technology had already modified, and now it is not keeping that gap as they are, or as what we had learned in your previous standard. Anyway, so thermal expansion is basically a change in your length with respect to your change in your temperature gradient. So thermal expansion is, let us say, alpha, and if you having two length of your rod L1 and L2 for a given temperature T1 and T2, then alpha will be given for the rod as a difference of L2 minus L1 upon your original length, so that is L1 divided by the T2 minus T1. So let assume that your initial temperature is let us say 0, so आपका equation हो जाएगा LT minus L0 upon L0 into given temperature. So most of the solid expand on the heating, and from the atmospheric point of view, it means that the average interatomic distance is increases as the temperature is increases. Roughly it is observed that the 12% is increases. Okay, so expansion, it is observed that it is 12% could be maximum. Now what it mean by expansion? So we had learned in last year there is a chemical bond or the bond strength and so on. So अगर आपका crystal, if your sample is increasing, that means the bond length should be also enhanced. So the total energy should be modified. So the bond energy is given by A by R raised to n. So it's the attractive energy, the plus is the repulsive energy. So n and m are the exponent for the attractive and the repulsive component. If your parabolic shape of your bond is very much identical, that means it is the uniform expansion, and suppose it is another side is become shallow, then you can say there is a asymmetric potential energy curve, and this is a symmetric potential curve. We have observed that in case of a ionic crystal and the covalent crystals, the expansion is almost symmetrical, whereas in the case of a metallic crystal, the your value of your m and n are little bit lower compared to the value of m and n in the case of covalent and ionic bond. So the exponential component or the power exponential factors, that is m and n, in case of a ionic crystal as well as covalent crystals are little bit higher, and therefore the right arm of your parabola potential curve is little bit steeper. लेकिन अगर value of n is high as in the case of a covalent, if n is a small, which is the case of a metallic bond, then your right hand side of your curve become shallow. That here you are finding the asymmetric. Asymmetric हुआ तो फायदा ये हुआ कि expansion of the bond length is little bit higher, and therefore in the case of a metal you are finding that the expansion response or thermal expansion response is higher compared to the ionic bond and the covalent bond crystals. Okay, so with this I stopping here and wish you all the best for exam. Stay home, stay safe, and do your best on the day of your exam. Thank you so much.